Imagine looking up at the sky and feeling for a moment that everything is frozen in place. The familiar constellations, the Milky Band of the Milky Way, that faint glow we barely notice. Now flip the switch. Nothing up there is still. Not the stars, not the galaxies, not even the very floor of space. The entire universe stretches slowly, like an elastic fabric that never stops yielding. We can measure this in light, the oldest messenger we have, because as it travels through an expanding space, its waves reach us slightly stretched, shifted toward the red. That small shift, the redshift, works like a timestamp. The farther the source, the more pulled the light is, the faster it appears to recede. And it's not that galaxies are sprinting across a fixed stage, it's the stage itself that's growing between them. That realization didn't come in a single flash, but from the sum of persistent observations refined over decades. To turn light into a ruler, astronomers rely on objects whose intrinsic brightness is predictable. Type Ia supernovae, for instance, explode with very similar peak luminosity, so comparing the observed brightness with the expected brightness reveals distance. Cepheids, pulsating stars whose rhythm relates directly to their luminosity, offer another cosmic yardstick. Spiral galaxies can also be used via the Tully-Fisher relation, which links rotation speed to brightness. When we layer reliable distances over the apparent velocities derived from redshift, an elegant pattern emerges. The more distant the object, the faster its recession, a relation that broadened what we used to call Hubble's law, and which today, with more nuance, is credited to Hubble and Lemaitre. Over the years, measurements became so precise that they revealed something even more surprising. The expansion isn't just real, it's accelerating. That acceleration points to a mysterious component we nicknamed dark energy, acting like a negative pressure that stretches space itself. It may sound abstract, but the consequences are concrete. In the young universe, matter and radiation were incredibly compressed. The tiny density ripples left by the primordial plasma, the so-called baryon acoustic oscillations, seeded structure formation. Gas had neighbors on all sides. Gravity needed to pull over smaller distances, and energy loss through radiation let clouds cool, contract, and light new stars often. As space stretches and matter spreads out, that dance changes tempo. Gas grows thinner, shocks and compressions become less frequent. Regions that could collapse take longer to reach the pressure and temperature conditions they need. The universe transitions from a noisy childhood with bustling stellar nurseries to a productive adolescence and, slowly, to a calmer adulthood where new births become rare. To visualize it, think of a balloon inflating with little dots marked on its surface. No dot walks on its own. They all drift apart because the rubber is stretching. The same happens to galaxies on large scales. On smaller scales, gravity still rules. Stars orbit galactic centers. Satellites circle planets. Clouds collapse here and there. But in the grand tapestry, the expanding fabric thins out material and cools the pace of star birth. This difference shows up clearly when we compare spirals and ellipticals. In spirals, the arms hold vast reserves of gas and dust. There, a small bump in density is enough for gravity to hook that region. Gas compresses, heats up, and when core pressure hits the mark, nuclear fusion ignites. In ellipticals, most of the gas was consumed, heated, and blown out by explosions or winds, or simply turned into stars long ago. The result is a glow dominated by older stellar populations, yellow, orange, and red. There's hardly any fresh material left to fuel new generations. As the universe keeps stretching, refilling that stock of gas becomes even harder. And the trend is for young light to give way to mature light. Every star is a delicate negotiation between gravity trying to squeeze it and the radiation pressure that nuclear fusion provides from the inside out. As long as there's fuel, typically hydrogen at first, then helium and, if mass allows, heavier elements, the star maintains balance and shines. The most massive ones live fast and bright. They build up very high core temperatures, burn fuel at a furious rate, look bluish, and end their lives in spectacular supernovae, forging heavy elements and leaving behind neutron stars or black holes. Stars like the Sun take a more measured path. They live for billions of years, expand into red giants, shed their outer layers in a soft, colorful glow, while the core collapses into a white dwarf supported by electron degeneracy pressure. Over countless trillions of years, that white dwarf cools and darkens, becoming an invisible ember. Red dwarfs, the champions of thrift, can burn for trillions of years thanks to their slow consumption rate, but the final fate is the same. In the end, cooling and silence. Add up this dynamic across millions of galaxies, and you get a hall where the lights are being dimmed, one by a patient caretaker. This gradual dimming lines up with a long-term scenario known as the Big Freeze over time. The activity that keeps the universe lively dies down. The average temperature drops, energy sources run out, and, on timescales that defy everyday analogies, even supermassive black holes lose mass through quantum effects like Hawking radiation. Think of 10 to the power of 100 years, a number that makes you dizzy just to consider. The end result is a sea of particles and photons so diluted that, practically, nothing happens on its own anymore. In even more distant versions of this script, physicists speculate about proton decay, which, if it exists, would accelerate the dissolution of baryonic matter, slowly unmaking the very substance of things. None of this changes tomorrow, nor in the next million years. But it's the kind of conclusion that emerges when we follow the logic of the equations all the way through. There is, however, the possibility that dark energy not only maintains the acceleration, but strengthens it over time. If this cosmic pressure grows more aggressive, technically, if its equation of state parameter evolves unfavorably, it could overcome not only the gravity between galaxies, but also the forces that keep solar systems bound and, in extreme scenarios, even atomic bonds. That's the big rip. The imagined progression is methodically unsettling. First, galaxy clusters loosen, then galaxies themselves come apart. Later, stellar systems stop being stable. In the end, molecules and protons unravel. Some estimates place such an ending around 10 to the 22nd power years, depending on how those cosmological parameters evolve. It isn't today's leading forecast, but it serves as a reminder that accelerated expansion isn't a footnote. It sketches the future in bold strokes. Elsewhere on the theoretical board, there's the idea of reversal. What if, through some still unknown combination, expansion yielded to contraction? The Big Crunch scenario imagines the cosmos returning to a state of extreme compression, where classical equations stop being useful and quantum effects take over. Some variations suggest a cycle: expansion, contraction, rebirth, like a heartbeat on billion-year timescales. Today, measurements of the microwave background, distant supernova, and galaxy distributions point to accelerated expansion, not reversal. Even so, keeping an open mind is part of the game. If science teaches anything, it's that models improve, and sometimes change, whenever better data arrive. When we talk about data, it's worth pausing to note how we know what we know. The standardized brightness of type Ia supernovae let us verify acceleration. Cepheids helped calibrate the distance ladder. The 21-centimeter line of neutral hydrogen lets us map cold gas and cut through regions where dust blocks visible light. The cosmic microwave background, the leftover glow from when the universe was only a few 100,000 years old, works like a baby picture of the cosmos, with small, hotter, and colder patches corresponding to over and under densities. Galaxy spectra reveal not only redshift, but also chemical makeup and average stellar ages. In parallel, numerical simulations with billions of particles trace the evolution of a web of dark matter and gas over billions of years, comparing predictions with observed maps. It's a gear train: observe, simulate, adjust, and over time, the picture sharpens. On human scales, relativity feels distant, yet it's tested every day. Satellite navigation systems like GPS only work because they correct, simultaneously, two effects: time dilation due to speed, special relativity, and time dilation due to gravity, general relativity. Clocks in orbit tick at a slightly different rate than clocks on the ground. Without correction, positioning errors would grow by kilometers per day. Experiments with atomic clocks flown on airplanes in the 1970s also showed tiny but measurable lags, proof that time is elastic. In the lab, particles in accelerators reach 99.999% of the speed of light, altering their proper time and living longer than they would at rest, an effect that's useful for studying them. And when we hear about faster-than-light motion, we need to separate illusions from violations. Relativistic jets, like those emerging from the core of the galaxy M87, can appear to beat light when seen at specific angles. What's happening is a combination of very high speeds, close to C, with the jet's geometry relative to our line of sight. Light emitted at different instants travels different distances to us, compressing the apparent time intervals. Math explains the illusion. Physics hasn't been broken. In reactors, the pools of water around the core emit that characteristic blue glow because charged particles, electrons for example, are traveling there faster than light can travel in that specific medium. That produces Cherenkov radiation, an optical boom analogous to the sonic boom of supersonic aircraft. And note the detail. Nobody broke the vacuum speed of light. The inviolable barrier remains intact. When scientific imagination goes further, two iconic ideas resurface. The first is the warp drive, inspired by Miguel Alcubierre's work. The proposal, in broad strokes, isn't to speed the ship past C, but to deform space in front and behind it, creating a bubble that surfs without locally breaking the rule. The hurdle? The original model needs absurd amounts of negative energy. An ingredient general relativity doesn't hand out freely, though quantum effects like the vacuum between plates, the Casimir effect, show that something negative can exist under very controlled conditions and on tiny scales. Recently, proposals have appeared that redesign the bubble using arrangements of electromagnetic fields and normal matter, arguing that perhaps we could approach C without invoking exotics. The gap between elegant equations and practical engineering, however, is enormous. Even if such bubbles could exist, designing, stabilizing, powering, and piloting something like that is, for now, a challenge that belongs in the realm of concepts. The other idea is wormholes, the Einstein-Rosen bridges. In movies, crossing them is easy. In physics, they tend to snap shut too quickly, demand exotic ingredients to stay open, and may be microscopic. There are conjectures that, at quantum levels, a connection between entanglement and geometry, ER equals EPR, might relate certain aspects. But that's far from becoming an interstellar highway. Meanwhile, quantum entanglement, often brought up in talks about instant messages, runs into the no communication theorem. Measuring one particle gives random outcomes, and only by comparing records later through normal channels do we see the correlation. No message is faster than light. If we zoom out, we see that matter in the universe organizes into filaments, nodes, and voids. Some nodes are so dense that, even immersed in expansion, they create currents that drag galaxies toward them. One such node, hidden behind the Milky Way's dust in a swath of sky called the Zone of Avoidance, became famous as the Great Attractor. It's not a single object, but a region with excess mass, stars, gas, dust, and above all, dark matter. We don't see it with traditional optical telescopes because our own galaxy blocks the view, but we feel its effect in the peculiar velocity of the Milky Way and its neighbors. There's a tug in that direction. To get through the dust curtain, astronomers use radio, the 21-centimeter hydrogen line, infrared, and X-rays. The Parkes Radio Telescope in Australia, with multi-beam receivers, did blind surveys that mapped thousands of galaxies in the zone of avoidance. By cross-matching those data with infrared surveys, it was possible to confirm a large galaxy population there, validating most candidates and leaving a residue still hiding in the dustiest regions. In that picture, the Norma cluster shows up as a likely central piece. Measured galaxy flows in the region suggest a deep gravitational well. Entire structures drain gently toward that node. There's also the structure known as the South Pole Wall, a colossal chain of galaxies, gas, and dust stretching for at least 700 million light-years, from the northern hemisphere to the far south of the sky. It's also partly hidden by the Milky Way, which delayed its identification. We don't see it directly in the night sky, yet its effects are detectable. Galaxies between us and the wall move away from us a bit faster, as if they feel the pull of the mass concentrated in the wall. Those beyond the wall move a bit slower, as if that structure's gravity holds them back. It's the cosmic web revealing itself, in slow motion, like a set of rivers channeling water along preferred directions. When we connect these discoveries with the concept of the Laniakea supercluster, the huge gravitational region our local group belongs to, we gain a more cohesive view of our cosmic neighborhood. islands of galaxies floating in seas of void, arranged by peninsulas and isthmuses made of dark matter and gas. To turn this mosaic into a coherent map, ever better distance and velocity measurements are essential. Projects like 2MTF estimate distances based on dynamical relations and help reconstruct the flow field around us. ASCAP, a precursor to the SKA, scans the sky in radio with unmatched sensitivity and field of view, revealing cold gas where we once saw darkness. The Taipan Optical Survey focuses on elliptical galaxies to refine the map in more distant regions. The sum of these efforts forces theorists to adjust models. On huge scales, general relativity still holds strong, but subtleties in matter distribution, the physics of black hole feedback, and, above all, the nature of dark energy may still hide surprises. Amid these structures, local stories matter too. Our local group, dominated by the Milky Way and Andromeda, is on a slow collision course. In a few billion years, the two galaxies will pass through each other, and, after a ballet of approaches and retreats, will merge into an elliptical or lenticular galaxy. It won't be catastrophic for individual solar systems. The chance of one star hitting another is tiny because, despite the glow, galaxies are very empty. But gravitational tides will reshape orbits, and the remaining gas could fuel spurts of star formation. Meanwhile, the local group floats within larger currents, feeling the influence of nearby voids and nodes. The so-called local void, a region of lower density, also contributes to our peculiar velocities. It's like rowing in a cove. The general tide pulls outward, but local eddies and countercurrents modulate the motion. Faced with so much concentrated mass and so many measured flows, the question asks itself, will the Great Attractor, with all that pull, swallow us one day? The short answer is no. Locally, over hundreds of millions of light years, gravity in those nodes directs motions. But the universe as a whole expands with acceleration. On very long horizons, the strands of that web grow powerless against the tide of expansion. Superclusters that seem cohesive today tend to fall apart. Each galaxy will grow more isolated over time. The Great Attractor's influence on the Milky Way will fade, like a current losing strength when the tide keeps rising. Here, it's worth revisiting the contrast in timescales. In cosmology, we talk about billions and trillions of years. In human life, we think in decades. The urgencies that matter for our future happen fast. Climate, biosecurity, clean energy, resilient communication, responsible space exploration. The same curiosity that taught us to read redshift gave us satellites that monitor forests, oceans, and ice, gave us sensors to forecast storms, gave us models to understand pandemics. The quest to understand stellar fusion inspired experimental reactors here on Earth. Studying asteroids led to orbital deflection tests, a form of planetary insurance. Techniques for detecting exoplanets help develop more sensitive instruments useful in other fields. In other words, reading the universe's light isn't a luxury. It's an engine of innovation that comes back home. In the end, the story is still being written in light. Shifted spectral lines tell how space's fabric has stretched. Colors and intensities outline ages, compositions, and dynamics. In infrared, we find warm dust. In X-rays, seething gas in clusters. In radio, the hydrogen that threads arms and filaments. Each part of the spectrum acts like a different magnifying glass. When we combine them all, we gain the power to put the sequence of events in order. Matter clumping, stars igniting, galaxies colliding and merging, black holes growing, the backdrop stretching, the cadence of births slowing. It's a long chronicle, built with care and persistence, that gives us something rare: context. It shows that where we are isn't a random fragment, but a temporary, luminous island in a changing ocean. It teaches that limits exist, like sea in a vacuum, and that even so, we can be creative within them. Optimize trajectories, study media, search for geometries. It points out that big answers don't fall from the sky. They're built with precise observation, tight theory, and a healthy dose of disciplined imagination. And it reminds us that the decisions that truly shape our tomorrow, unlike the universe's thermal fate, depend on us. We may not choose between the big freeze and the final rip, but we do choose how to use science today. What technologies to pursue, what risks to mitigate, which problems to face head-on. Maybe the best way to wrap up is with a simple mental picture. Imagine the cosmos as a slow, wide river. Superstructures, the Great Attractor, the South Pole Wall, Laniakea, are like eddies and backwaters that guide the water locally, organize the currents, create shortcuts and passages. But the whole river flows to the sea. Accelerated expansion is that inevitable flow. We can learn to read the bends, measure the speeds, understand the vortices. We can build better boats, choose safer routes, and avoid rocks. The sea, however, still lies ahead. What's on us, while ancient light still arrives and our instruments grow more sensitive, is to keep alive the curiosity that brought us here. Because it's what lights up on one side the map of galaxies, and on the other, the path to a wiser future on our small blue dot. If this kind of journey through space and time stirs something in you, here's an invitation. Share your questions in the comments. Say which cosmic scenario you find most plausible and why, and take a moment to subscribe and leave a like. That helps a lot to keep this mission alive, translating the universe into clear, engaging language for more people. Today, the light telling us the story of the cosmos is faint and distant. Tomorrow, it might be your curiosity clearing the way to the next discovery. Thanks for watching, and see you on the next journey.